Hello class, this is Mr. Hart, and in this podcast we want to start our lesson on electric fields. Okay, and an electric field is something you may have heard of, but it's not a word we use a whole lot in our just common vocabulary when we talk to people. And it has a very specific physics definition we want to talk about. Okay, and so let's just get right to the definition so we can kind of make sense of what an electric field is. Okay, so an electric field, okay, is a way of describing the strength and direction of the possible electric force in any given area from the presence of charges. Okay? Note that I put possible electric force. Okay? And let me explain why that is. Okay? So let me just give you an example. Let's say I put a positive charge here, and it's 1 Coulomb. Okay? Then let's say that I put another charge here. Okay? And it's a positive charge. We don't know how much charge it has. Okay, regardless of how much charge is on this guy, right, and how far away it is, we know that this 1 Coulomb charge is going to push in this direction on that charge over here, right? So there's an electric force that it's going to put on this guy, right? And it would put one on him, but let's assume that this guy's not going to move. Okay, it's going to put a force on this positive charge over here. Okay. Now that's regardless of how much charge it has, right? So we could have said in reality, before that charge was even there, that 1 Coulomb charge right here was pushing in that direction, or will push in that direction. Okay. And because it's close, it's going to push with more force than further out. Okay. And so again, it's kind of the possible electric force. So we can draw the electric field for one charge, even though it's not putting electric force on anything. There's nothing else to put an electric force on at the moment. But we can say, well, we know it's going to put an electric force in this direction if something's on this side, if it's a positive charge, okay? And if it's really close, it's going to be a stronger charge, okay? If it's closer here, right? If it's on the top side, it'd go this way, right? And we can kind of draw this field, okay, that helps us visualize what the charges are doing, how they would be pushing out if other charges were present, okay? So you can imagine a positive charge pushes all the arrows out like this, okay? In comparison, though, a negative charge, you would expect to do the opposite, right? If I had a negative 1 Coulomb charge sitting right here, you would expect the opposite. If a positive charge was placed somewhere in this field, okay, the arrows would go into the negative charge, okay, because they would be attracted to the negative charge. Okay, so electric field is always described for what would a positive charge do if it was placed in this field, okay, and so forth. Okay. So that's what an electric field is. It's trying to visualize and describe how these things would move, how they'd behave even before they get placed in this field. Okay, let me pull up a simulation that kind of shows this and how we can see interactions between charges. Okay. Okay, so this is a FET simulation. It's cleverly called the electric field of dreams. Okay, based off an old movie, if you remember that at all. Okay, but let's say we place this. This is a 1 Coulomb positive charge, and we can see how in the nearby area of this charge, okay, wherever we place it, the arrows are always pointing out. Any positive charge that would be placed in this field, okay, would be being pushed out basically, right, by the electric force. Okay. And you'll also notice, right, that the arrows nearby the charge are a lot longer than the arrows that are further out away from the charge, right? Because there'd be more force the closer you are to this charge, right? So this is kind of a visualization of what the electric field would look like, okay? And then likewise, if we change this to be a negative charge and add it to the field, you would expect all the arrows to point in, right? They're going to move into that negative charge if a positive charge was placed in this electric field. Okay? And so there we go. That's how an electric field can be visualized. Okay? Now you may be wondering, this is all great and dandy, but why is this useful? It seems like there's only two possible configurations. Okay. Well, it turns out that electric fields are most useful when we're trying to describe the interactions between charges. Okay. So let's go back to our 1 Coulomb positive charge right here. Okay. So if it's just sitting here, right, we know that the arrows are going to be pointing out like this, right, because any charge would move out away from this guy nearby. But let's say now there's another positive charge right here, okay, and it also is emanating out like this, okay. So what's going to happen in this middle area? Because now if a charge gets placed right in the middle of these guys, okay, if it's get placed right here, then it would be perfectly balanced between these two charges, right? It would have exactly the same amount of force from this charge as it would from that charge, right? And so right in the center, there would be no force acting on this object, okay, or on this charge that would be placed right here. And then if it was in the center like this, it'd kind of go straight up like that, okay? And if it was in the center right here, it'd go straight down like that, right? Because it's getting pushed down, but still in the center between these two objects, okay? So instead of the field continuing to go out like this, we kind of hit this barrier, okay, where things start moving outwards but never really reaching the center point because it'd be perfectly balanced between the two, right? So you get this interaction that's occurring. And so this is really cool to kind of visualize that the force starts to kind of go in this direction and push it more away in that direction, away from both the charges like this, okay? That's something that would be hard to describe without an electric field, without visualizing, okay, how these two charges are interacting one with another, okay? And then it's really cool because now we can kind of think about trajectory. If I put a charge right here, okay, you can kind of imagine it's going to kind of want to head in this direction because it's going to see this charge and kind of follow these arrows, right? As well, so I put one this way, it kind of follow these arrows and go up in that direction, and so forth. We can kind of start drawing trajectories of other particles that get placed in this electric field, okay? So that's pretty cool. Let me do one more commonly described electric field. Let's do a 1 Coulomb positive charge and a 1 Coulomb negative charge, okay? So now this electric field will look slightly different. This right nearby him will still be going out like that, okay? And these will still be going in like this, okay? But now in the center, now it's getting pushed away from this guy and pulled towards this negative charge. So now you can actually go straight towards this, okay? And these arrows, instead of going out forever in that direction, will now start to get pushed in, okay? Kind of making a path like this towards that negative charge, okay? And I'm not being precise. This is mostly conceptual, right? But now again, if you think about trajectory, if we put a positive charge right here, it kind of will follow these arrows and head towards the negative charge, right? And so you start to get kind of these arc shapes that head towards the negative charge, okay? But that's a positive charge, negative charge electric field, okay? And so you can do all sorts of these guys. You could put, 4 protons in the same field or 4 positive charges. You could put 4 negative charges, 2 positive, 2 negative, put them in different places. And even in all the chaos of how much force is interacting on these guys, you can still describe pretty well how they're going to behave, what trajectories they're going to have. So it's really cool. It's a really powerful tool. Let me pull up the simulation one more time so you can see how well you can kind of visualize these things, okay? So if you just have one charge, it's not that interesting, right? But let's start adding some more charges, okay? So these are 3 negative charges. Let's add some positive charges in there, okay? So that's a positive charge, okay? And you can see they can get kind of crazy looking, okay, with all the different field lines. But now you can at least say, well, if I put a object in here, a charge in here, where is it going to go, right? And so if we put, let's say, a positive charge somewhere right here, we can kind of just follow the lines. Let me do a better color. Say we put a charge right there, then you can just kind of follow the lines through and kind of see what the trajectory would be. So that charge would go right there. If I put one right here, let's say, it'd kind of follow these lines and go towards that guy. Okay, this guy right here may go straight up and then it hits a barrier and then goes back down and goes to that one. Right, so we can kind of look at all the different behaviors that are going on, okay, and make these pathways, visualize how these electrons and positive charges, negative charges would behave. Okay, so it's really cool. It's a great way to visualize what's going on without having to do a whole lot of calculations, right? In fact, no calculations. You're just kind of drawing the arrows for individual particles and seeing how they interact. Okay, awesome. So that's your what your lab is based on. Okay. I have the separate sheet that you need to do the lab, to complete the lab, but you can just get it from me. But it will be drawing these electric fields and using another simulation where you can kind of practice with electric fields. Okay, but hopefully that all made sense. Let me know if you have any questions, and thank you for watching.